This discussion will be on Poisson's and Laplace equation. Okay, Poisson's and Laplace equation. So why we need to study this equation is what we will discuss initially. Okay, just to know, because so far we have calculated electric field intensity, that is E vector, or electric flux density, that is D vector. Okay, if you remember whatever we have discussed so far, we have calculated these two using electric field, Coulomb's law, Gauss law, right? Gauss's law, Coulomb's law, and potential field, right? In the sense, if V is given, you can calculate as E equal to minus del V. So you will get E. From that, you can use D is equal to epsilon E and you calculate a D, right? So that way, either you can apply Coulomb's law or you can apply Gauss's law, right? Point form of Gauss's law, del dot D is equal to rho V, those equations. So you can apply them and find electric field intensity, flux density, okay? But in a given region, is it not? Whether it is electric, whether it is application of Gauss's law or whether it is application of potential field, the region should be given to you. Means you should know from where to where you have to integrate, right? From R varies from 1 to 2, theta varies from 0 to pi by 2, phi varies from 0 to 2 pi. Remembering? So it was covering a region, right? Closed surface, inside the volume, all that. Clear? So whatever we have found, okay, field intensity or flux density, whatever we have calculated so far, is for entire region or for a space. Okay, we first calculated for a small surface, small volume, then we integrated for a bigger volume, bigger area. Remembering? So this is how we have done it. Okay. Now, always it is not a possibility that you will have a region or a space to find these values, right? E vector, D vector. They may ask you to find E vector and D vector at a particular point, okay, or a small area. So whenever, whatever method we have used so far, if you try to find E vector and D vector, you will have to find it for a bigger area only or a bigger region only. Unless you do volume integral rho v dv, you cannot get the total charge. Unless you get total charge, you cannot find what is E vector, D vector. Okay. So whatever we have studied so far is applicable only for space. In the sense, a bigger space, a bigger field, a bigger region. Okay. But practically, this will not be the case, right? That's why we have studied boundary conditions. Yes or no? We have studied boundary conditions. In boundary conditions, we know that those conditions are true only at the boundary between two fellows, boundary between air and conductor, or boundary between two dielectrics, right? So we have derived it, we have done few problems. In that problems, you might have understood that we are finding E vector, remembering capacitance, derivation of multiple dielectrics, all that. What I'm trying to say is, whatever we have derived so far, or numericals what you have done so far, is all more theoretical or more assumption based. But in the real case, you will have only a small area or a boundary to apply all these conditions. So then you have to, or such problems are known as boundary value problems. So you have boundary conditions which you have already studied, but that alone will not help you always. Okay, so you should have Laplace and Poisson's equation, which are true only for boundary, only true at boundaries. Okay, boundaries means a small area or small length. Okay, so Laplace and Poisson equations are used to solve boundary value problems, that you have to understand. Okay, it cannot be applied for a region, area, volume, not possible. Remember that. Point form of Gauss's law, we know that. From point form of Gauss's law, we know that del dot D is rho V. Correct? We know that del dot D is equal to rho V, where D is flux density and rho V is volume charge density. Now by this time, we are thorough with this, right? And we know that D is epsilon E. Right? We are thorough with this one. Okay? Even in dream, if somebody asks you what is the relation between D and E, you will be shouting, right? D is equal to epsilon. So now for this D, you substitute this. Whatever, yeah. So E is minus del V. Okay, this also a del V. Okay, this relation also you know. So please substitute it here. So this equation becomes del dot epsilon minus del V equal to rho V. Equal to rho V. Okay. Now I rearrange this. I'll take this minus this. Okay, del V equal to rho V. I hope it's very clear. We started with Gauss's point form, that is del dot D is equal to rho V, and D is epsilon E. So substitute there. So I get del dot epsilon E equal to rho V. Then I realize that E is minus del V, right? My negative gradient of potential minus del V. So I substituted minus del V there. Okay, then I have rearranged the equation just to get minus epsilon into del V equal to rho V. Okay, so let me continue. I'll bring this minus epsilon to the right hand side, RHS. So this equation becomes del V equals minus rho V by epsilon, right? Because I bring this minus epsilon to the RHS. So I got del V equal to minus rho V. Okay, now this del, okay, this is del dot del. Okay, this del dot del operand, okay, means it is gradient of gradient. Okay, del is gradient, right? Remembering del operator is gradient for scalar operand, right? Getting the for vector operand it is divergence. So V here potential is scalar operand. So for scalar it is gradient. So it is gradient dot gradient. Gradient dot gradient can be written as gradient square. Okay, because it is scalar operation. X into x is x square. So similarly, del dot del is del square. Okay, so this is known as a del squared operand. Okay, del squared operand. Del squared operand. Del squared. So this I can write it as now del square V equals minus rho V by epsilon. Clear? Okay. Put it in a box. This is Poisson's equation. Over. Very silly. This is Poisson's equation. Okay. So del square V equal to minus rho V by epsilon is known as Poisson's equation. Okay. And just now, while introducing, I told you that. Yeah, tell me. Somebody called me, sir. Not audible. Somebody want to talk to me? Any doubt? Okay, I'll continue. At the beginning of this, before starting this derivation, I told you that Laplace and Poisson's equations are not applicable for entire region, right? We will not be concentrating on region. Okay. So in most of the cases, in practical cases, for small region, okay, when I say region, it is a small line or small area kind of, okay. So in a small region, this volume charge density may be 0. Okay, like dielectric medium. If you consider a dielectric medium, you don't have there any charges, right? You don't have any charges. So in practical conditions, mostly what you have is dielectric medium, right? Conductors are less, right? If you look around you where you are sitting now, how many conductors you will find? You will find more dielectrics than conductors. So practically, this universe is filled with dielectrics more than conductors. So when you take general case, in most of the regions, okay, the volume charge density or the charge free regions will be more than charge existing regions. Okay. So what I'm trying to say is, you have to now assume a region where the charge density is 0. That is, volume charge density is 0. That means in this equation, rho v becomes 0. That's what I'm trying to say. Okay. Now this is Poisson's equation. You know, del square v equal to minus rho v by epsilon is Poisson's equation. Okay. So that tells you that Poisson's equation is applicable only in charge existing region. But it is not true that all the regions will have charged particles, right? Usually in some insulators or dielectrics, we may not have free charges. So in such cases, this rho v will be 0. So if rho v is 0, what happens to this equation? If rho v is 0, what happens to this equation? This del square v becomes 0, is it not? Because rho v is 0, 0 by epsilon will be 0. So del square v will be, put it in a box, this is Laplace equation. This is Laplace equation. Happy? Now you know why students love these two equations. Very easy to derive, very easy to remember, and it's a repeated question. So why will not somebody love it? You fall in love with it, right? Yeah, you are in love with it now, right? See your notebook. The derivation is very straightforward. Okay, you have to just substitute two results which you have already studied. D is equal to epsilon E and E is equal to minus del V. You will get Poisson's equation. And once you get Poisson's equation, you have to just assume that there is a charge-free region. So in charge-free region, rho v equal to 0. That means del square v equal to 0. Then you will get Laplace equation. Okay. So always remember, Laplace equation is applicable in charge-free region, and Poisson's equation is applicable in charge existing region. Okay. And this del square is also known as Laplacian operand. Laplacian. That also remember. Del squared operand. Okay. For Poisson's equation, it is known as del squared operand. And for Laplace equation, it is known as Laplacian operand. Okay. Del square is known as Laplacian operand. Okay. But you know that field theory will not be that easy. Okay, that straightforward. So why this Laplace equation becomes complicated, or Poisson's equation become complicated, is this del is, you know, del is what? Gradient, right? So this del square operand can be in 3 coordinate systems, right? Del square can be in Cartesian coordinate, del square can be in cylindrical coordinate, and del square can be in spherical coordinate. So you should know what is this, because v will be given to you like 20x square plus something, or 200r by 200r into sine theta something. So if v is given like that, then you should know how to find del square of that, right? To solve numericals. Okay. So in Cartesian coordinate system, del square is represented as, it's a straightforward. Okay. In Cartesian it is a straightforward. In Cartesian coordinate system, del square, okay, del square v is represented as partial difference square. That's it. Del bar square v by del bar x square plus del bar square v by del bar y square plus del bar square v by del bar z square. That's it. Okay, you know that gradient is del bar v by del bar x, del bar v by del bar y, and del bar v by del bar z. That you know already, right? So this is square. So just to put square for partial. So 2 times you have to find double partial differential. Okay. So square of x, square of y, and square of z. So you have to double partial differentiate potential with respect to x, with respect to y, with respect to z, and add them. So you will get it in Cartesian coordinate system. Okay. When you go to cylindrical coordinate system, this equation becomes cylindrical. Okay. In cylindrical coordinate system, this becomes 1 by rho del bar by del bar rho into del bar v by del bar r plus 1 by rho square del bar square v divided by del bar phi square plus del bar square V by del bar z square. So this is in cylindrical coordinate system. Okay, so this is how you represent the Laplace equation. If you write equal to 0, it becomes Laplace equation in Cartesian coordinate system, Laplace equation in cylindrical coordinate system. So next let us see what is Laplace equation or what is del square V in spherical coordinate system. Okay, how to represent del square V in spherical coordinate system. So in spherical coordinate system, del square V is 1 by r square del bar by del bar r square sine theta 1 by r square sine theta del bar by del bar theta sine theta del bar V by del bar theta. Okay, plus 1 by r square sine square theta 1 by r square sine square theta del bar square V divided by del bar phi square. Okay, so it is necessary to remove.